Greetings, folks. Hey, Gavin. Hey, Graham. Good
Hey,
to see
Marisa. Hey, everyone.
So this is a pretty big day. It's our final Rockin Pop-Up ever live on Facebook. How do you guys feel about that?
It's bittersweet. We've had a lot of fun doing these virtual Rockin Pop-Ups, and I think that we hope that they've reached a wide audience, and we've had fun doing them. So kind of a tough day.
Yeah, we're sad to see it go, but happy that it's not really goodbye. You guys are sticking around and just going to be doing different things with the museum. And I wanted to just take a moment before we get into today's presentation, which is about the solar system, big topics. So we'll get into that in a second, but we do want to just mark this occasion and really thank you both for all of the work that you've put into connecting our community with geology. It's been amazing. I've got this image that I found from the archives, which this is from 2019, our Earth Day event with the city of Santa Cruz, and we were celebrating the Earth's birthday, another big topic. So the origin of the Earth, which is kind of what we're getting into today. It's kind of appropriate. And you guys have these wonderful birthday hats that we made. So there's been so much that you guys have done for the museum over the past 4 years that you've been volunteered, including these past 2 years of doing these online presentations, which have been so great. We've got, I think, around 35 recordings, which can go on in perpetuity for people to continue to learn about geology. But you've also done walks and these pop-ups and rock ID days and blogs and so many things behind the scenes that we're so grateful for. And we're grateful that you are also going to be continuing your relationship with the museum. And one way that we wanted to really emphasize that continued relationship is to present you both with a little gift. And so on behalf of the Santa Cruz Museum of Natural History, where you both have been loyal volunteers for the past 4 years, we would like to mark this moment with 4 years of club level memberships for both of you. So it's you're joining the club, and it's a way for us to say that this is not the end. This relationship continues on, and Graham, you're on the East Coast now, but this type of membership gets you admission to science centers all over the country. And so just continue this good work wherever you are.
Thank you so much. Oh, and I'll definitely be back to give you all a visit.
Wonderful. Yeah, and it's been nice that because we have this virtual series, we've been able to continue to have you looped in even after you made your big move to the East Coast. So it's great. But we want to make sure that you guys know that we're so grateful for the time that you've put into this series and the years prior to going virtual as well. So thank you both.
Yeah, thanks so much, Marisa. And we also, before we jump in, it's worth noting that these virtual pop-ups were really a three-person team. And so thank you as well for help making them.
It's been so fun. It's been great getting to know you guys better, and also just learning about geology. It's such a gift that I am able to tune in for these programs every month, and for a while there every week. And I'm also going to now drop in the chat a link to a survey. So for those of you who have been tuning in for the Rockin Pop-Ups, or even have come to in-person programs with the Geology Gents, we have this survey that we would love to get some feedback from you guys about. And I'm going to let Gavin and Graham share a little bit about why we wanted to do this survey.
Yeah, so me and Graham, as Marisa, you said, we've been doing this for 4 years now, and we've done a lot of different types of museum events and things of that nature. And because we are working in academic spaces and want to continue to be educators, we are going to be doing an evaluation of the things that we liked and the things that we would do differently. And we're going to be sort of doing a critical evaluation that we'll write up as a publication in a sort of an education facing journal. And so we're hopefully going to use any responses to this survey from folks who have tuned into these pop-ups at any time throughout the past 2 years as a way to do a sort of a qualitative evaluation. So we'd really love to know what you all think, and the survey, which we think is going to be pretty quick and to the point, will be one of the ways that we do that. So yeah, we'd appreciate it if you have opinions one way or another, if you could share those with us in the survey.
Cool. Yeah. And, wait to do that until after we get through the topic of the day, so maybe now's a good time to take it over.
Absolutely. I messed up my screen sharing though. Could you give me permission again?
Yes, there we go.
Thank you. All right. So yeah, we are going, for our finale, we're going to end with the beginning. And so we've talked about so many different aspects of the Earth system. And so we thought it would be lovely to finish by talking about kind of how the Earth got here in the first place.
Yeah, that's right, Graham. This is going to be a good one, really good one to end on, especially in this 3-part series. So why don't we, before we jump in to what we're going to talk about, kind of talk about how it fits into the rest of the last 2, right?
That's right. Sorry, my computer's clicking around a little bit here. Yeah, so we're thinking about our solar system, and we're in our 3rd part of this 3-part series where we look at the different planets and components of our solar system. So 2 months ago, we talked about the terrestrial planets. Last month, we talked about the giant planets. And so, Gavin, we've kind of got this idea of like what planets are like, but there's so much more, right?
Yeah, and this is honestly something I didn't really know until grad school, but you're totally right, Graham. Like, the solar system is not just the planets. There's a ton of other stuff going on and interesting things to know, not only about the sun and about the planets, but also about all of the rest of the stuff zooming around this part of the galaxy.
Yeah. And so one of the, certainly we've talked about these different planets, but really the fixture of the solar system, the main event, if you will, is our sun.
That's right, Graham. Yeah, the sun really makes it all happen in a way, right?
It really is, and it really is it's the center of attention and really the main course of the solar system. And a lot of folks are familiar with this. One of the wild things about the sun is it sits up in the sky as this big bright orb, but it is actually made out of gas.
Yeah, not actually solid. That's pretty neat. And a lot of what we know about it is through observations, right? And I find it really cool. The image that you have here, depending on how we observe it, we see different things about it. So we can see the surface, and that's sort of like the atmospheric component of the sun. But you also have 2 other images here on the left. Do you want to?
Yeah, absolutely. Yeah. So when we look at the sun with different wavelengths of light, those are essentially different colors, but colors of light beyond the colors that we can see. You can see different parts of the atmosphere. It's like how, our sky looks red on an afternoon, but it looks blue when the sun's high up in the sky. It's the different way you're shining light and what light's kind of getting through. We can see different levels of the sun by looking at these different colors of light. And one of the coolest things about the sun is that, we're so used to it. It's this, fixture that we're always can kind of count on. But the sun is always changing. And so in the photosphere, the part that we can see with our eyes, so we should never look at the sun, it'll hurt them. But if you look through a telescope with the right filters on it, and those filters being very important, by looking at the sun with these filters that protect our eyes, we can see these different ways that the surface of the sun is changing through time.
That's right, Graham. You could see motion, and this motion to the trained eye is actually very familiar. It looks like heat moving to me. When I see this, it looks a lot like heat moving. And so, Graham, this is maybe a good opportunity to say, why is the sun so hot and why is the surface moving in these little orb-like ways?
Yeah, that's right. So the sun, the surface that we can see, using these filtered telescopes and things like that, it tells us that there's heat, and the heat is coming out of the center of the sun, because the sun is actually a nuclear furnace, and the heat coming out of the interior comes from nuclear fusion. So the sun is made up of mostly hydrogen, which is the lightest element of the periodic table. It's just one measly little proton. And through a series of nuclear reactions that occur at high pressures and high temperatures, those protons fuse to form helium, the next lightest element, and reduce a ton of heat.
Yeah, a lot of radiative heat here. And so that, as I like how you put it, it's a nuclear furnace. This is nuclear heat, similar to how nuclear reactors on Earth work.
Yes.
Yeah. Okay, go ahead, Graham. Sorry.
Oh yeah, no. Yeah. So the sun is able to generate all this heat. We know this is super important for weather, climate, life, those little things that really matter to us on Earth. But in the grand scheme of things, our sun is just a garden variety average size star.
Yeah, that's right. It's kind of funny. We look to the sun as our sun, right? It's so special because it's the thing that's given us life in the solar system. But you're right. When you kind of put some perspective on it, it's sort of, I don't know, I wouldn't say, it's just kind of interesting to think that there is a whole galaxy, billions of these stars, all throughout the galaxy. So we are just a little part of it, a measly speck. But Graham, I like this picture you have here on the right. So the sun there are a lot of similar stars. It's a garden variety stars, but all stars are not the same, right? The sun sort of like fits in the middle, both size and heat wise, between red dwarfs and blue giants.
Yeah, that's exactly right. So some stars are really, really big. Some are smaller. Medium-sized stars of ours they sit in the medium realm of size and heat. And so, yeah, it's and right around the size of our sun is kind of what most stars tend to look like. And there's a very many stars in our galaxy alone. So our galaxy, like you said, Gavin, it's got hundreds of billions of stars. That's the Milky Way that, if we can get to a nice high ground with not a lot of light pollution, we can see that bright streak across the sky. And this little dot here, this is where we live. This is where our sun sits in the Milky Way. If you squint real close, you might be able to see it.
Right.
Yeah.
So basically, we started out with the sun, and in the history of the solar system, you also kind of start out with making the sun. But what happened before the sun? How did the sun form?
Yeah, that's a great question. And so the sun, the Earth, all the stuff that makes us up, it all started out as stardust. So nebula, or nebulae in the plural, these are these clouds of mostly gas, mostly hydrogen, a little bit of helium, and then the littlest amount of dust. But these are enormous clouds of gas, and we've been able to image them around the galaxy and in the universe with various telescopes. But these contain hundreds of thousands of suns worth of material. And so these are these enormous clouds of gas, and it's all very diffuse. It's very, very low pressure, but kind of this is where it all begins.
Right. So basically, before we had a sun, before we had the planets, before we literally had anything in the solar system, all of the matter that makes up the solar system was just a big cloud of gas and dust.
That's exactly right.
Wow.
And so, but then, something had to start it all, right? Like we know we're not just a cloud of gas today. Mm-hmm. And what probably started that off was a nearby supernova. And so what happens is you start with this big cloud of gas, and something sort of squishes it, perturbs it, and that could be a pressure wave from a nearby supernova. And that starts to get it starts getting it to kind of fall together. Gravity starts to pull the different bits and pieces of the gas and dust together. And as that starts to collapse, Gavin, what happens?
Well, you get to all of this gas and dust kind of forms a flat plane. And the reason why it's forming a flat plane like that is because you start to form your star at the center. So you, again, just to reiterate, you have this gas cloud, something perturbs it to where it collapses on itself. And at the center of that, you start to form a star with high heat and high pressure. That star, our proto-sun, has a bunch of gravity, and everything starts to orbit around it, just like our planets are orbiting around it still to this day. So you collapse this gas cloud because of the gravity of that star at the center, and it forms a disk. That's our protoplanetary disk.
Yeah.
Graham, one thing I actually just wanted you to touch upon is, for those at home who aren't familiar with supernova, can you just give a quick synopsis of what that is?
Yeah, so supernova is when a star explodes. And so certain stars that are big enough, when they get to a certain age, they become unstable. So they actually collapse into themselves and then bounce back out. And they're these super, super powerful energetic explosions. There are nebula today that are these enormous, kind of interestingly colored, clouds that are up in the night sky. We can't see them with the naked eye. We need telescopes to catch an image of them. But they're these sort of really energetic moments of destruction when a star is destroyed. Sometimes these can be the predecessors to black holes, though not always. And for anyone who might be worried about our sun supernovaing, no worries, our sun isn't big enough. It'll probably never do that.
Got it. So we were talking about the protoplanetary disk, Graham.
That's right. Yeah. And so I just wanted to take a moment to sort of show another image of what that looks like. You've got things spinning around this central point of the sun. It's flattening out. Our sun is just igniting in the center. And so we've got this cloud of gas and a lot of dust now. And this is where things start to get really interesting.
Okay, Graham. So we have the protoplanetary disk, we have dust, but this dust starts to coalesce, right? Things just, because you are sort of consolidating this gas cloud now into this disk, inside the disk, the dust starts to accumulate. It starts to interact with other dust particles, and you get to boulders, you get to planetesimals, which are when all of these boulders accrete into one another, and then we're all the way to the planets we see today.
That's right. Yeah. So in this protoplanetary disk, we build our way up to planets. And you don't really need anything that much more special than good old-fashioned gravity to hold things together. And it starts to be really light interactions between small particles. But as it gets bigger and bigger, we start to get gravities of things like the Earth or the Moon. And those can be really good at holding these clumps of rock together.
Okay.
And so yeah.
Okay,
go ahead, Gav.
I was just gonna put this into a quick perspective, because when I started to learn about these, I was like, okay, this is a cool story, but this happened 4.5 billion years ago, and it's not like based on the rock record like a lot of the geology we learn about. So I feel good about the fact that a nebula started it, because we can sort of model that with computers, and we see a lot of evidence in the chemical records of our solar system bodies, but also the disk is something, the nebulas and the disk are something that we can see with telescopes happening in other places in the solar system, right, Graham?
That's exactly right. Yeah. And so, yeah, we've been able to image protoplanetary disks far away. And I think, you can see that it's round. You can see that it's brightest in the center where we've got our sun starting. Or the star here starting. The sun is our star. All other stars are just regular stars. But what's really cool here is there are these little gaps in the dust here. And these gaps are probably feeding zones for planets. So where you see a gap in the dust, there's probably a planet that's growing up in there.
Huh, so cool. It's very similar to how like Saturn's rings are forming and have gaps and things like that. So
That's
it's a
right.
disk. Yeah.
Yeah, so you can see these kind of parallels across different different scales, which is also a nice thing. It helps you kind of trust these models a little bit more.
Yeah.
So that's essentially how we get to our solar system with our planets. And there's a little bit of complexity, and by a little bit, I mean a lot of it. But one of the biggest things that kind of is going on here is the closer we get to that sun, the hotter things are. And so in the places close to the sun, like where the Earth and Venus and Mercury formed, it was too hot for things like water and different ices to hang around. But as you get further away from the sun, it gets a little bit cooler, right?
That's right. And so we call that the frost line. And so there's this arbitrary distance away from that sun in the middle where you can start to get things like ice forming beyond that line, but it's too hot for any of those volatile elements, we call them, anything that will evaporate away to form within that frost line. And so this harkens back a little bit to our previous two pop-ups on this stuff where, yeah, there we go. Thanks, Graham.
Yeah.
Where, the terrestrial planets in the center are smaller and rocky because they formed within the frost line. They only have that rock, less of that volatile material. But away from the frost line, you get the giant planets because those have all of the gases that would have been lost within the frost line.
Yeah. So this gets us to where our planets are, and this is what we talked about in the last couple of pop-ups. If you haven't seen those, check them out. But there's more than just this. And we talked about the sun, but there's more than even just the sun. And so if we go way out beyond the frost line, there's all sorts of awesome icy, dusty things in the Kuiper belt and the Oort cloud.
Huh. These are two new words, Graham. Okay, so the Kuiper belt is basically still part of that disk, right? But it's way far out. And you have things called Kuiper belt objects. So this is an area where we have obviously smaller than planetary sized stuff, but up to protoplanet size, or not protoplanet, planetesimal size.
No, protoplanet and even what folks call dwarf planets. So folks who are big fans of Pluto were probably disappointed when Pluto was decided to no longer be a planet, but to be a dwarf planet. But Pluto also is known as a Kuiper belt object. So it's a member of this Kuiper belt. And so if you look into this model here, this innermost red ring is actually Jupiter, Saturn, Uranus, and Neptune. And so here in this cloud of all this good, icy, dusty stuff is Pluto. And Pluto's a great example of a big, icy, dusty Kuiper belt object. But
got it. Sorry.
The Kuiper belt is this teeny tiny little speck compared to the enormous Oort cloud, which is the home to things like comets. And so, we can start to keep looking out further and further to these bigger and bigger scales. And the Oort cloud is mostly theoretical. We don't have telescopes that can view the really dark objects out there, but we know it's there because we get things like comets that pass by the sun and by Earth.
Okay, so this is pretty far out, Graham, literally like far out from the sun. And so it makes sense that most of these things are dusty and very icy. And so that kind of fits in with what we know about Pluto. So Pluto being a Kuiper belt object, and then the Oort cloud being mostly things like the comets that we're presenting here. Yes. Right. So it's not a disk, the Oort cloud. It's sort of like just a ball of stuff coming from all directions. And that stuff is comets. And what are comets made out of, Graham?
Ice and dust. These things formed out in these really cold parts of the solar system. So, good old fashioned rocky, carbony dust, but then different ices, not just water ice, but nitrogen ice. So it's like the air we breathe, but it's so cold that it's frozen. Methanol and formaldehyde ices, these weird organic molecules. So all sorts of interesting things. And so these usually live way, way out in the solar system where they're so cold that these ices hang on to them. But every once in a while, they swing in close to the sun on their orbits. and then they really put on a show, right, Gavin?
Right. So every comet we see is kind of like an Icarus. It's flying too close to the sun, and because it is, all of those volatile elements, the waters, formaldehyde, methanol, those are actually volatilizing off. And when I say volatilizing, I mean actually evaporating or sublimating. So they're going from solid to a gas. They're also breaking little tiny chunks off, and that gives comets those really sort of indicative tails.
That's right. Yeah, these bright shining tails that are just reflecting all that sunlight off of them. But we don't need to go as far out as the Kuiper belt and Oort cloud to see some really cool parts of our early solar system. Just between Mars and Jupiter are all these chunks of debris that we call asteroids, and all together we call it the asteroid belt.
Okay, so Graham, this is something that was kind of surprising to me when I first learned it, because when I first heard about the asteroid belt as a kid, I figured that's also pretty far out. But it turns out the asteroid belt is actually smack dab in the middle of Mars and Jupiter, which is kind of interesting.
That's right.
And the fact that it's closer in than the Oort cloud, say, means that it's more terrestrial, right? You get more rocky stuff rather than like really icy stuff, right?
That's right. That's right. You've got more ices in here. Yeah. And so we actually know a little bit more about asteroids than we do even some of the planets in our solar system, because sometimes when we're really lucky, chunks of an asteroid will fall onto Earth in the form of meteorites.
Right. So meteorites are, and I know, Graham, you love these because this is kind of your thing now, what you do for your research. But meteorites are these little vestiges, these little capsules that archive what all of these asteroids are made out of. And so I like that you have here both the asteroid and the meteorite that probably goes with it. So we're actually able to study these rocks so much that we can kind of, to some confidence, link them to a specific asteroid they came from, which is kind of cool. Can you explain to us how that happens?
Yeah, absolutely. So we can look at different asteroids with telescopes, and by looking at the different light that reflects off of them, we can say something about what they're made of. And then a meteorite is just a rock. So we can take it into a lab and study its chemistry. We can do all sorts of awesome things to study it. We can measure it. We can, observe the textures of it. And so by getting these really close looks at pieces of meteorites on Earth, we can compare those to that information from telescopes and actually start to relate some things to each other. And so meteorites come in a bunch of awesome shapes and sizes and textures and compositions. We'll talk about that in just a little bit. But the other really cool thing is that not only do meteorites come from asteroids, but they also come from planets.
This is just wild, Graham. You have actual rocks on Earth that we can say with pretty good confidence came from Mars. Mm-hmm. It's pretty cool.
Yeah, and a ton of what we know about Mars comes from these rocks.
That's right, because we don't have return missions yet. So, but we know that we know somewhat what those rocks should be made out of, because we have meteorites that have broken off Mars and made their way to the Earth. But not only Mars, the Moon. And what about this one? Can you explain?
Yeah, so this is still a topic of debate, but I thought we thought it was too juicy to leave out. And so there are some bits of rock that have been found on the Moon that scientists think might be from Earth. And while we don't know for sure if some of these pieces of lunar rocks are from Earth, we know that if chunks of Mars and the Moon are being knocked onto Earth, probably chunks of Earth from time to time have been knocked onto these different places.
Perfect for your Martian geologists, Graham.
That's right. Keep your eyes peeled for that rare Earth rock when you finally get to Mars.
Okay, so that's interesting. So meteorites are these little capsules that we can learn about Kuiper belt objects. And so, Graham, what can we tell about about sorry, I meant to say not the Kuiper belt, the asteroid belt. What can we learn about the asteroid belt from meteorites?
Yeah, and so when we look closely at meteorites, we can start to see some really neat things. And so this one group of meteorites, my favorite personally, are called the chondrites. And these are really leftover bits of that dust. So this is really just dust that kind of got squished together. Some of it heated up, maybe some water melted and flowed through it, but that's really it. So all these different, textures and pieces in here, these are chunks of that original dust or bits of the dust that, melted a little bit or got disturbed. And so a good way to think of them is like sandstones, sedimentary rocks that formed out of that, the dust and the particles of the early solar system.
Wow. So these are actually, when you say dust, you mean that like protoplanetary dust, the first solid forming in that disk. And so these are really important because they, when planets form a lot, they heat up a lot and they change the rocks. But these rocks haven't been changed. So they're like the chemical compositions and sometimes the textures of those first things forming in the solar system, right, Graham?
That's exactly right. Yeah. And so, among the neat things are even these like separate chunks of metal that aren't mixed in with the rock. And so that's one thing I just want to point out because we'll come back to this in a little bit. But we know that there are whole asteroids that are essentially like giant chunks of this original dusty material. And so Ceres, or one Ceres, is the biggest asteroid in the whole asteroid belt. And so up here, this is comparing Ceres to the moon and Earth. And so it's not even close to the size of the Earth, but this is big for a dwarf planet. And this is basically just one of these chondrites. It's got these chunky bits of that dust together. Waters were able to melt in there. So this formed outside the frost line and incorporated water ice, and that melted. And so while the outside surface has dried out and is pockmarked with craters, there's salty water that makes up this interior level. And so, there's all sorts of neat things that that we could certainly learn from like a trip to Ceres, in addition to trips to the moon or Mars.
Huh. Okay, Graham. So basically it's like those chondrites because it never got hot enough to where it differentiated or melted, right?
That's right.
It's just that original stuff, no change. That's pretty interesting. It'd be cool to go there one day.
I would love to. If you're ever on the way, let me know. I'll bring snacks.
Sounds good. But what about are all of these asteroids like this or no?
No. So some of them got hot, and they got hot enough that most of the moisture evaporated away. And you're left with this soup of molten rock and molten metal. Remember, I pointed out those chunks of metal in that other chondrite. And that metal was heavy enough to sink. And so we've got metal at the center and molten rock, hot rock on the outside. And I bet this is starting to sound familiar to some people out there.
That's right. Okay. So we call this differentiation. And this is exactly what happened on Earth to make Earth's core. And that's why you have layers of different types of rocks on the Earth, our core and our mantle and our crust. This actually also happens to certain asteroids that get big enough and hot enough. And so some of the different types of meteorites that we see, we can tell they come from different parts of these differentiated bodies. So do you want to take us through that, Graham?
Yeah. So out on the outside, these are igneous rocks. They are volcanic or they're granite-like. They are distinct. They definitely didn't form on Earth, but they really look a lot like igneous rocks on Earth. There are also meteorites that are made out of metal, and this metal has cooled really slowly. So it's actually allowed crystals of metal to actually form in here. So you get these awesome intersecting patterns here. And then there are even some meteorites that formed right at the boundary between the mantle and the core. And so you get this mix of metal with these big chunky olivine crystals. And the olivine is the same thing that Earth's mantle is made up of.
Yeah, that's so cool, Graham. And it's cool to have these meteorites that we could put back to the process of differentiation, because as many folks know, if they've listened to our other Rockin Pop-Ups, we know that the Earth's core is iron and nickel, but we've never been able to sample any of those rocks. And so these are probably a lot like what those rocks in the deep Earth look like.
Yeah, that's exactly right. And this is a great window to kind of understand the hard to reach interior of the Earth.
Mhm.
And so there's an asteroid out there that probably the most famous asteroid is Vesta. It's about half the size of Ceres. And though it is, just a tiny little piece of rock compared to the Earth, it has all the same major features, planetary features of Earth. And I'm not talking about oceans and continents. I'm talking about a metal core and a rocky mantle and crust.
Huh. Pretty interesting. So these aren't too different from Earth.
No, in an astronomical context, not at all.
There you go.
So Gavin, let's try and bring it all together. We've gone about as far away from Earth as you can within our solar system, but this all these components kind of help us understand Earth, right?
Yeah, that's right, Graham. So basically our understanding of the birth and the making of the solar system really all comes from observations we can make from our telescopes. And so we talked about our nebulas and our protoplanetary disks, and those are things that not only do we model with computers to say that happened, we have chemical data from all of the stuff we can look at in the solar system to tell us that happened, and we can also observe that happening in other places in the galaxy. Then when we want to understand why the planets look the way they do, why some are terrestrial, some are large, we can think about the frost line, and that again is a lot of what tells us that happened is mathematical models for how heat is distributed in the early proto-solar system. But of course, we have chemistry to tell us that as well. The fact that we have volatile elements around. And then finally, Graham, your favorite, the meteorites. And I'm always very compelled at how the meteorites can not only tell us what stuff is made out of, but the processes happening, and also how you distributed different elements in that early solar system, and how the heat and the processes happening in that early proto-solar disk really sort of shaped how it looks today, right?
Yeah, that's exactly right. And so, one of the things that's so cool is that we can look to space and the solar system to understand how Earth formed, but Earth has also been a part of its solar system through its entire existence. And so, infalling pieces of our solar system, meteorites, there have been important asteroid impacts on Earth through time. Probably lots of the water on Earth came from comets early on, and some of the chondrite rocky chondrite asteroids. And so, Earth, we can look to the solar system to understand how Earth first formed, but it's also been a part of the solar system. And, even to this day, if it weren't for the daily sunlight and the way the Earth changes its orbit around the sun, our life on Earth would be entirely different if it existed at all.
Yeah, that's right, Graham. And for the keen folks at home who have been watching this and listening to us talk about the frost line, I think this is kind of why we threw this slide in there, right? Because if we were within the frost line, the early Earth probably didn't have that much water, right? All of the water within the frost line evaporated off. And so this goes to your point about how Earth changes a lot of the time, especially in the early Earth, by what's hitting it. Mm-hmm. And so that's where we got our water, probably, is what hit it, those chondritic materials.
Yeah, chondrites and comets. Yeah, and thank goodness too.
That's right.
Well, Gavin, I think we've done it. I think we've covered our 3 chapters, and I gotta say it's been a great ride.
I agree. I think that first and foremost, we've just had so much fun putting these together, right? Like we obviously have to thank all the people who have viewed the virtual Rockin Pop-Ups and who have sort of shared in that fun, because really the reason we do these things is because we love geology and we want to share some of the things we learn, because the more we learn about the natural world, the more we can accrue that knowledge, and it makes, you know, going through it and observing it even more special and interesting the more you know. Do you agree, Graham?
Absolutely. And Gavin and I, we've come on here as experts to talk about this, but with every new week and every new theme, it was a chance for us to also learn and grow. And has always been like so much fun for, us to start with something we know a little bit about and learn a little bit more. And it was always just so exciting to be able to come and share these things with all of you and share your excitement for rocks. It's been great to talk geology with a bunch of geology loving folks.
Agreed, Graham. Agreed. And maybe a final note we can say is just thanking the museum, and of course we've thanked Marisa, and Marisa has very much been a part of this team and has really made it happen. We've researched the topics and presented them, but we wouldn't have been able to put these virtual Rockin Pop-Ups on without Marisa. And in a more general sense, the infrastructure the museum sort of provides us in the community, and getting engagement and having us put these things on in the name of the museum has really helped us achieve our goals for what we want to do, right? We want to make earth science education accessible, and we want to, for lack of a better term, just share in the excitement of it, while maybe providing some new cool information for you viewers. So thanks to you viewers. We really appreciate people who've tuned in, and really thanks to the museum for giving us this opportunity. It was a really great time.
Couldn't have said it better. We could not have done it without you all at the museum to really make this happen.
Well, it's been our pleasure, and it is really important to us that we are able to connect our community with the local scientists and land managers and people who are out there doing the work, and also inspiring community members to see where they fit in to that world too. And I know you both have inspired so many rock lovers out there, and people who didn't even know that there are rock lovers of all ages and all backgrounds. And one of the things I'm really excited about is, like we mentioned earlier, this is not the end. We're going to continue to work with you both, and really wanting to try to connect even more people from the Earth and Planetary Sciences Department up at UCSC to the museum, because we do realize that this is one of the greatest services that the museum has to offer, is being a community connector for people in academia, for people who are doing the work. But it's just so important to connect that work with the community. So we're just going to be finding more and more people to do that with, and with the help of Gavin and Graham. So just thank you guys both so much. And I'm happy that we have these recordings that will live on. So, I mean, who knows how many people at the end of the day will be learning from you, including all of the people who have met you in person at the museum and out in the community. And it's such a gift. So thank you so much. And I think, is this it? Is this the end? Is it the time?
See you later.
And I'll just note, if you do want to, Graham, you're not going to be involved in this one, but Gavin is going to be out and about in the community on April 23rd at the Climate Action Market at the Seymour Center. He's going to be representing the museum with a booth there. So again, it's not the end. There's another occasion just on the horizon. So, and if you do have a chance to fill out that survey that's in the comments, we would very much appreciate it. And it'll go directly towards that academic work that Gavin and Graham are doing to evaluate this experience and hopefully help future science communicators. So,
yes.
Thank you all so much. Goodbye.